My name is Mike DeLaCluse. I'm president of the Lesman Instrument Company. I'd like to thank all of you for taking time out of your busy schedules to join us for Safety Systems 102, Safety Instrument and System Sensors, presented by United Electric Scott Pierce. Today we'll help you understand what the difference is between SIL-1, SIL-2, SIL-3, and what you need to know to build a safety instrument and system. We'll also help you understand the language of safety instrument and systems, including the acronyms and standards. Scott Pierce is our presenter. He's a senior regional sales manager for United Electric, having spent 3 decades applying pressure and temperature products to alarming and shutdown systems in the chemical, petrochemical, and oil and gas industries. We will be muting the phone lines. If you have any questions, there is a question tool built into the GoToWebinar bar on the right-hand side of your screen. Please go ahead and type it into that tool. I'll get the question, and then I'll try to stop Scott if it makes sense at that period of time to answer the question. If not, we'll hold it till the end, and we'll get all your questions answered at the end. So with that, Scott, I'm going to let you take it away.
Michael, thank you for the introduction. I appreciate everyone tuning in to this webinar. My goal today is really to touch on the surface of safety instrumented systems, give you, as Michael said, just a little background, some concepts, and some terms of what is going on in the world of safety instrumented systems. It is a 102 presentation. We really will not get into any calculations or any discussion of calculations. However, as Michael said at the end, we'll answer some questions. My contact information is spierce@ueonline.com. Should you want to email me in the future, also feel free to do that. What we're going to do today is really talk a little bit about why do we need a safety instrumented system. We're going to look at a lot of acronyms today, the SIS, SILs, RRFs. If you haven't been in depth or studied any part of safety instrumented systems, these things can be a little bit overwhelming, but I'll try to clear some of the smoke and mirrors and give you a clear definition of what some of these things are. So we'll be defining SIS. We're going to determine the safety integrity level. We'll look at some of that. As I mentioned, the acronyms, and then also some of the key issues driving this industry today. There's a balance within the process control, oil and gas, and power industry today that we need to look at the beginning of this presentation. And that balance between safety and throughput is important. You know, the stockholders of these great firms are demanding profits. We have to maintain the assets in good working order, and then we have to keep a good, solid corporate image as manufacturers. However, we've got the other side of the balancing act, and that is we've got society, employee safety, which is paramount, community safety, and then the environment, which is also paramount, that we have to guard over. So what we end up with is this incredible balancing of process safety and process uptime that we have to maintain. And I've heard it said before, safety can become a very heavy burden on manufacturing, and the cost is high, but yet we still have to maintain this balance. And this balance, by the way, is not felt just in the U.S. This is an international direction for process, chemical, petrochemical, and refining. And oddly enough, a heavy push from this industry is coming from the international arena. So that's where we're seeing quite a bit of implementation at the skid builders, the compressors, the reactors, and so on and so forth. The specs are being driven from the international market strongly. Why are safety instrumented systems important? Well, I think that this is a pretty easy question to answer. we've all seen this sort of picture possibly in the past, and that is we're working in very volatile applications and facilities. Safety is paramount, and the other piece of the puzzle is humans control it. We do, and we certainly do make errors. And so we need to mitigate or minimize the element of errors that can occur in these facilities. And so we're going to talk about embedding systems within our manufacturing that can keep our systems or our processes at a safe state. I want to talk a little bit about process control versus safety. The difference between the two is significant, but yet sometimes not difficult to separate. A basic process control system continuously operates the process in the plant during normal startup, running, and shutdown phases. But the safety instrumented system brings the plant to a safe state if hazards are existing. Kind of like the anti-lock brake system on our cars. When we have to go into an immediate stop, the anti-lock brakes kick in and brings us to a safe forward-facing stop in most cases. However, there's something very important about this whole world of safety instrumented systems. There is really two driving standards, if you would, that drive the whole practice of safety instrumented systems. So when properly designed, they would be built around an international electric code or an international standard called 61511. And then there are also some internal functions or internal standards that are used that are proven in use type standards. So there's two that exist, and then of course you may have heard S84 before, but I think we're going to focus in today on IEC 61511 as our driving standard for safety instrumented systems. Now, as I clarified earlier, that these two standards or these two practices exist in close proximity to one another. In front of you, you'll see a schematic of a steam turbine, which has its basic process control loop set up here, as you can see. But what you'll also see separate from the basic process control system is this outer loop of instrumentation we're going to call our safety instrumented system, consisting of three elements, which we'll talk about shortly. But again, it's important that we don't confuse basic process control with safety instrumented systems. They are two totally separate but equally important entities to the process. The purpose of a safety system is to bring the process to a safe state. You may have heard this called in the past an ESD. We'll talk about that in a moment. Or permitting the process to continue in a safe manner when all specified conditions are satisfied. Some examples of that would be an emergency shutdown device, the ESD that I referred to just a minute ago. Safety interlocks, safety shutdown. Although many of us don't like to hear the word shutdown, sometimes it's imminent, and we'll talk about that. And then also starting permissives. Is the boiler good to start? Are our processes ready to go? Are doors closed and hatches closed when they need to be? These starting permissives are also very important. Now, I talked about the element of this international standard called 61511. That 61511 applies very specifically to the chemical, petrochemical, power, oil and gas industry. That is the standard that contains all of the practices and the measurements to determine how to build a safety instrumented system. But what rides closely or moves closely to 61511 is another standard called 61508. These are two very important standards to understand. 61508 applies specifically to the manufacture of the instrumentation or the hardware or even software for a safety system. So very important to know that in the example of a transmitter in a sensor application, that sensor instrument, which is only one piece of the overall SIS, must comply to 61508. And 61508 is a very interesting standard because it really starts for the manufacturer way before the creation of a safety instrumented system or a safety instrumented function device. To clarify that, it means basically that there are certain organizations that can come in and look at manufacturers of instrumentation and be able to measure whether or not that company, that corporation, even has the engineering expertise to understand and design a safety function device that has the layers of protection it would need to comply to 61511. I bring this up because it's important when you're looking for instrumentation or pieces to your safety instrumented systems. Make sure those companies are 61508 certified, and those would be certified by outside governing bodies like EXIDA or TUV FM. So just giving you a little background on 61508 and its importance. I'm going to start breaking down quite a few of these acronyms that bounce around and hopefully try to clear some of the confusion behind them. We're looking at a slide right now that talks about the difference between safety instrumented systems, SIS, and the difference between a safety instrumented function, which is SIF. The safety instrumented system is basically the overall system. An SIS system, if you would, safety instrumented system, is composed of any combination of sensors, logic solvers, and final elements. Now that makes up the overall safety instrumented system. However, on the flip side, looking at the SIF, the SIF, that is a safety instrumented function, and that is the method by which the risk of a specific hazard is reduced automatically using either a sensor, logic solver, and a final element. But a safety instrument function will be one of those three items specifically. So there's the difference between an SIS and an SIF, both playing completely different roles in terminology, just as basic process control and SIS do. So a simple example of what a SIS would look like. This is a safety instrumented system. It consists of three safety instrumented functions: a sensor to your left, a logic solver in the middle, and a final element at the end. Those are your three core pieces to what we're going to be talking about today. Now, determining the need for a SIS is quite complex. From the beginning stages of design, the user has to conduct a hazard and operability study. That's the HAZOP, to determine what types of failures or malfunctions that could occur in a given process. So this hazard analysis, once completed, will lead us to the decision of whether or not a safety instrumented system is actually required in this process. If it is required, then what happens at that point is we have to then decide what safety integrity level is required for the process. So we have a HAZOP rating. We know that it will require some safety instrumented systems within it. And now the next piece of the puzzle is, what will that SIL, that safety integrity level, be required for the process. And then once we determine that, the user can use a variety of different techniques for this, including levels of protection analysis, which is very, very common practice in our industry. And we call that LOPA, layers of protection analysis. We're going to come back and look at this whole issue of SIL, safety integrity levels. And but before we do that, I want to talk a little bit to what a LOPA is and what this layer of protection analysis looks like at the end. So I've put together a little drawing here that that is my best way to describe what a LOPA is. We originally started out with the design of the process, which we talked about, and that could be at the engineering level. Somewhere within our organization, we've determined we're going to design a process. And within that, of course, that design of process has basic process control systems or basic process control elements. We have determined that there is some HAZOP to this basic process control. So the next piece to this LOPA is going to be to develop or design a safety instrumented system. Remember, that's the mechanical devices that are going to take action to bring us to a safe state. But what if those don't work? What's the next layer of the LOPA? Well, the next layer is going to be mitigation. That's going to be passive walls, dikes, and layers to protect outside of the SIS should something go wrong. But what if it goes way wrong? Well, then the last part of the puzzle out here with the layers of protection analysis is the response. Response basically is not what we like to hear, but plant and community actions. What do we do now? The worst case scenario has happened. And to bring that a little closer to home, I like to talk about, how do we apply this to the car we drive? We look over to the left here and we see basic design, process control, prevention, mitigation, response, which I showed you in the previous slide. We see how it compares to the process industry, which we talked about, but really to bring it to the simplest of simple, we could say, well, you know what? I've got to buy a new car. What kind of new car am I going to buy? If I'm going to do off-roading, it's going to be a 4x4, but in my case, I got to haul the family around. So I'm going for the minivan. Next piece of the puzzle is, well, now that I've got the vehicle, I've got to control it. I've got to get it to point B. Gas pedal, transmission, engine, all those things that you take for granted, that's what we're going to use. And how am I going to control it? Well, it's the steering wheel, the brakes, and I've got the anti-lock brake system. So that fits in with our world of SIS, if you would, alarms, interlocks, SIS functions. But going to the mitigation piece, and this is something my wife always tells me. I say, slow down, you're going too fast. And she goes, don't worry, I have bumpers, and airbags. Well, that is our mitigation point in a car. So we have layers of protection analysis in our cars. It's bumpers, airbags, crumple zones. And then the worst case scenario is, if one of those has to take a mitigating operation or correction, the worst case scenario is we've got this response, which is OnStar, cell phone, police, fire, ambulance, kind of things we don't like to hear. But this LOPA is important to understand as we start to peel away this onion skin and get into now some of the other acronyms that we're going to hear about as it relates to safety instrumented systems. So this safety integrity level that we talked about just briefly already, SIL, we've heard SIS, we've heard SIF, safety integrity function or safety instrument function. We've heard about LOPA. This SIL piece of the puzzle is very important, and it stands for safety integrity level. It is a measure of the performance and reliability of the individual safety function of an instrument. So SIL is a measure of performance and reliability of the SIF when it is called upon to do its job. Now keep in mind that these devices may sit for 5 years, they may hopefully sit forever and never be called upon. But we need to know that they're going to be functional and working when they are called upon. And we're going to talk about some of those challenges as we move through here. SIL, safety integrity level, can only be specified for a loop, not an individual device. So anytime you hear someone that might come into your office and say, I just found the greatest SIL-2 rated device, raise your flag up, put the brakes on. There's nothing rated in this business. Keep in mind that all of what we're going to be talking about is either certified or suitable. Those are the only 2 words that are really acceptable. There really is nothing rated. And you cannot say a system is safe or unsafe. You must define the amount of risk within the process that is tolerable. And we're going to talk about those numbers. We won't get into the calculation of those numbers, but we'll define them today and their importance as we go through this webinar. Now, when we look at these SIL numbers, there are 4 categories of SIL, and they're based on a 10-time reduction of risk at each level. Looking through here, you're going to see on my chart below, you've got SIL 1, 2, 3, and 4. I've never been involved in a SIL 4. I've never seen a SIL 4 in the process industry. So we're not going to talk about 4 today, and I've seen some SIL 3, but the most acceptable in a economic picture today is SIL 1 and SIL 2. There are some SIL 3 applications, but they're extremely costly to implement. And so we won't get into much of that. We'll focus in on SIL 1 and 2. SIL 1 is just basically minor property and production impact. SIL 2 would be major property and production impact, possibly even injury. So we'll focus in on those. Now when you look all the way over to the right, you're going to see another acronym that you haven't seen yet, which is called RRF. That's a risk reduction factor. The risk reduction factor is an important implementation to this whole puzzle. And you'll notice that I've got some factors there, and I'm going to focus in on the SIL 2 right now, which says that the risk reduction factor for a SIL 2 certified device should be anywhere between greater than 100 and less than 1,000. I'm going to talk about that. We'll define that here in just a bit, what I mean by that. So basically, the SIL level, the safety instrument level, is defined by the likelihood of a failure within the safety system. So probability of failure on demand, which is another acronym that we're going to be getting into, and its reciprocal, the risk reduction factor, are key pieces to the safety instrumented discussion. So remember, PFD, probability of failure on demand, and the reciprocal risk reduction factor of an instrument is critical, and the impact of such a failure on the system is known as a hardware fault tolerance, HFT, and safe failure fraction. Again, all important pieces to calculate the device that's needed to get to the level of protection also needed. So let's take a look at some of these and break them down a little bit. In a system that is passive under normal operating conditions, the probability of fail on demand average tells us the average probability that a device won't work when called upon, that this is expressed as a decimal, which is times 10 to the negative 3. So the risk reduction factor is a reciprocal of that probability of fail on demand. So for instance, In an example I'm going to show you here, if the risk reduction factor is noted as 806, then the probability of failure on demand average, which is important because we're taking the average, not the peak, would be 1 in 806. So putting this application that we're talking about of this example into the SIL-2 level, which is a device we're going to have to find in the industry that has a risk reduction factor of over 100 and less than 1,000, protecting us from major property and production impact and possible injury, is a SIL-2. Now once we determine that we're now looking for a SIL-2 device, and by the way, that those numbers, that the risk reduction factors and some of the other, the failure in time, the probability of fail on demand averages, all of these numbers can be found from a manufacturer's FMEDA. So failure mode effect diagnostic analysis are where these numbers are found, and those are the numbers that can be used in the calculations. We'll look at some of that here in just a bit, but wanted to let you know that. All right, so the hardware fault tolerance, which we touched on just briefly, is a measure of redundancy built into an instrument or the system. And so we'll see these hardware fault tolerances anywhere from 0, 1, 2, and 3. And so just to break them down, a 0 is the device or system loses its ability to protect if any single component fails within that safety instrumented system. So if you have a hardware fault tolerance of 0, you lose any piece of the puzzle within that safety instrumented system, you have no protection. If it's deemed that a hardware fault tolerance of 1 is required, then a device can still function properly if any one component fails. And we would see this, I'll use the example of a sensor. You would have dual redundancy for the sensor. Now past that, we have the hardware fault tolerance of 2, which is pretty common in our industry. This hardware fault tolerance of 2 means that I basically have triple redundancy in play. A device can still function if 2 separate components fail. So, you know, the thing we have to keep in mind in safety instrumented systems, if we have one component of that safety instrument fail, we have no protection. We're operating without brakes, so to speak. So it's important to consider the risk and that determination of hardware fault tolerance. Can I afford to be down, or can I afford to run this process without any protection? And what I see most common in our industry is a hardware fault tolerance equal to 2, which is triple redundancy. Now we're getting into the subject of safe failure fractions. That's the SFF. And if your head isn't spinning with acronyms yet, we're not done. So there's quite a few of them there. And so I want to talk to this whole element of safe failure fraction, which is very important in what we do. A device failures can be broken down into these 4 blocks that I have. We almost kind of looked at this in the LOPA, but now I'm breaking this safe failure fraction down into individual components. And so for ease of discussion, I'm going to talk of what I know best, which are transmitters. So we'll talk about this as a sensor, a transmitter in a safety instrumented system. The 4 blocks I show you basically call out safe detected, safe and undetected, dangerous and undetected, and then dangerous undetected. All instruments or safety instrumented functions have this breakdown. If we're looking at a safe and detected calculation or number, those are going to be numbers in a FMEDA, a failure mode effect diagnostic analysis produced by a third party for an instrument that basically gives us what will happen if this device is safe and detected. So what that means is basically if I've got a transmitter and it has a problem with it which falls into this category of safe and detected, it's just a nuisance. It could be just a display segment missing, but the product's still going to function, and it's visually detected. It may be detected in a proof testing interval or something to that effect, but it's not going to affect the device. It's going to still protect you. The next piece of this puzzle is safe and detected, or undetected, I'm sorry. This is also a nuisance, but safe and undetected also means that it may be just a normally blank display. Again, a segment gone. It could be visibly a menu that isn't coming up, but the device itself isn't damaged. Then we have dangerous and detected. Dangerous and detected is an important number, because what we want to know here is this is a serious situation that's going on with this instrument, but proactively the device is telling you that it's in a bad or dangerous condition. So dangerous detected would be a very smart instrument that said, I'm out here protecting you, I'm going down, and I'm going to let you know I'm failing. And that's typically done by either a saturation in the analog or a digital output. Then there's dangerous undetected. This would be in the case where it's very serious, and this is a device that has no means to tell you that it's failing or failed other than a proof test interval, which is something we don't want to rely on when it comes to instrumentation for safety instrumented systems. These calculations or these numbers are found in your FMEDA, and they're very important to have a definition on and know. Now, moving on in defining the safe failure fraction a little bit more is important to understand. The safe failure fraction of a device, it's determined by analyzing all of the possible failure modes in that product. So if it's a transmitter, what are all the possible failure modes? And then determining how each of those failure modes falls into 4 categories. And then we add those categories up, except for the dangerous undetected faults. We divide those by the total number of possible faults, and that gives us a percentage of diagnostic coverage. So an example I have here covers the terminology we just looked at: safe detected, safe undetected, dangerous detected, and dangerous undetected. In our case with this transmitter, we're looking at a 95% safe failure fraction, which is a pretty good score. What it's telling us, if we look at all the FMEDA data that was provided on that instrument by a third party, it's going to give us calculation numbers which are going to be numbers that are called FIT, or failure in time. Those failure in time numbers are really calculated out in billions of hours. So what we're looking at right now is a safe failure fraction of a device of 95%. And the way it's been measured, if you look at the calculations, is there is 63%, as you can see, safe detected. So anything that could go wrong with this thing, 63% of the time it's going to tell you. There is also 18% safe undetected. It still can run, but the only way you're going to find this, say, missing segment or what have you, is through a proof test. But you're okay. It's still safely running. But we get into this dangerous detected mode of 14%, which is 14% of this instrument that is not visual, that could cause it to fail, will tell you either via a saturation of the namer output, say in a 4:20, or perhaps a digital output, a human interface output to the device. It will tell you that, uh-oh, I failed. You need to come out here and replace me or repair me, and at least you know prior to your proof test interval. And then there is in this device 5% dangerous undetected. So 5% of this device has the ability to fail without you knowing it until you get to your proof test interval. So this has a safe failure fraction out of the box of 95%, which is acceptable and good to know. Now we have to take these safe failure fractions and put them together with the hardware fault tolerance. Remember we talked about hardware fault tolerance? So the chart below that I put together shows the relationship between a safe failure fraction and a hardware fault tolerance for very complex instruments, electronic devices like, let's say, a transmitter. The higher the safe failure fraction, or the higher the hardware fault tolerance, the higher SIL rating that's achieved without redundancy. So what we're looking at in this case that I have here, if the device you want to use has a safe failure fraction of, say, 92% and a hardware fault tolerance of 0, which means it's a standalone device, you'll need only one for a SIL-2 application. So we see the safe failure fraction falls between 90 and 99%. Hardware fault tolerance is at 0. Then a SIL-2 classification or certification is acceptable for this application. But if you had a different SIL or a different safe failure fraction, then you'll see the number and a hardware fault tolerance, say, of 1, then you would need to change over to a SIL-3 application. So again, this kind of chart will give you an idea of how the hardware fault tolerance and the safe failure fraction works together. We'll come and talk about this in the next couple slides a little bit more.
Hey, Scott.
Yes, sir.
One of the questions that came up is somewhere in there you dropped in the SIL, the product would have a SIL rating. And
yes, sir.
I think what you really meant is that and this is very difficult even to make sure that you get the wording right, because you got to get it right every time. And Exida really gives you a certification
correct
on the SIL rating. Well, yeah. And I see even I just screwed that up.
It's a very difficult, yeah.
They give you the SIL certification that gives you the safety factor, failure fraction that gives you the SIL level.
Correct.
And you gotta try to get the word rating completely out of your vocabulary, even though that's a very tough thing to do.
It's difficult, isn't it? And
is that,
as I stated,
did I explain that right? Because one of the questions that came up is I thought a device could not have a SIL rating, and a device really doesn't have a SIL rating. It has a safety failure fraction, which gives you a certification.
That is correct.
And then you have to go look at the chart to see where it falls in terms of the SIL ratings.
So we
because
did our
the product
job.
Doesn't get it.
You're right. We did our job at the outstart of this webinar. I said, don't listen to anybody that says SIL rated. So it is a very, very difficult discussion to get into, and kudos to that person that found me saying rated.
Dropping the word rating in there
because it is difficult, but it is true.
Right.
You've got
so it really all comes back to somebody like Exida doing a test on the product, giving you your safe failure fraction that gets you to your SIL level, right?
That's 100% true, right? All of these numbers, when someone comes to you with an instrument and says, as we said before, I'm SIL rated, or even if I'm SIL certified, or even SIL suitable, there has to be supporting documentation from either Exida, which is most commonly used, or TUV, It may be TUV for some of our European instrument manufacturers, or FM. Mostly you're going to see exit in TUV. However, Michael, as you stated, the numbers are very specific in these documents, and they're rated at, they have failure rates that cover all of the dangerous detected, safe undetected numbers or titles, categories. So these, and they all come out as failure in time. These failure in time numbers are calculated out in billions of hours, and it's important to have that supporting document and not listen to somebody like me that just stepped on my knuckles and said rated, because it's very true, very true.
Do you have an example of an Exodus certification at some point in the presentation? Because it may clear it up when.
I don't actually have a document in front of me, but I will provide a link to one that you can take a look at.
I've actually got one pulled up on my other computer, so at the end, if we want to show one, we can show one.
Excellent. Thanks.
The other question that came up is mean time between failure the same as say failure fraction, and I think the answer to that is no.
No, it is not.
Mean time between failure is part of Exodus or whatever approval agency or certification agency you use. It's part of their calculations, but they're by no means the same.
That's correct. Mean time between failure is not the same. What you'll find, again, is just not to be repetitive, but once you get into a failure mode effect diagnostic analysis, you'll see numbers that are calculations for failure in time. And so there is no real mean time between failure. These are average numbers that come about in the manufacturing process of a device. And there's also other additional measuring, there are other standards of measurement used outside of mean time between failure, and we have to look at how communicable the device is, or how susceptible the device is for someone making sporadic change or an unauthorized change in a device. So we'll cover a little bit about that, but I hope that does answer mean time between failure versus.
Yeah, sorry to take on that little sidebar, but I think the questions were there, and I wanted to get them answered.
Right. Thank you. All right, so let's take a look at some of the sources of the SIS failures. This is always kind of interesting because you look at these devices out there, whether it's a sensor, a logic solver, or the final element, and you go, what could possibly go wrong? I've bought the best instruments, the best valves, the best logic solvers known to man, and what keeps me up at night? And that's what could go wrong, because they are in sometimes awful environments, very, very corrosive environments, and they're connected to, in some cases, some pretty critical processes that have corrosive properties as well. So sensors, final elements, and all these things are susceptible to something that could go wrong, even being used as a ladder in some cases. So anything can happen. So what I did is I went back and I put together this little pie chart that kind of gives you an idea of where the breakdown falls in these devices and where the highest safe failure fractions are required. And it is interesting that the logic solver is put in one of the most protected environments, clean from the processes, and there's no moving parts, so they tend to last a long time and are very reliable in a safety instrument system. But the one SIF that we have to pay attention to is that darn final element out there, the one that requires a lot of proof testing and requires a lot of attention because it's almost 100% mechanical. It's 90% mechanical. So did the valve seat, did it partial stroke, and what does a partial stroke tell us anyways, and so on and so forth. So The final element is really kind of the biggest headache of the whole safety instrumented system. And then we have the sensor. The sensor is also very critical, but sensors can, in some cases, deliver very, very high or significant safe failure fractions. So in some cases, they could buy us some points on final elements that have poor performance as a safe failure fraction. But for my study today, we're going to stay focused on the sensor and what high safe failure fractions with a sensor can deliver in a total safety instrumented system. So to improve the safety system, in addition to improving the reliability of the devices themselves, there are a number of ways that designers, SIF designers, like ourselves, can improve the overall reliability of a system. And some of those things basically fall out in the sense of diversity. Diversity is extremely important in my eyes and in many eyes of the designers that are putting these safety systems together. And we'll talk a little bit about that diversity here in a bit. Redundancy is also extremely important to achieve the high safe failure fractions and to achieve the hardware fault tolerances we need in some of these applications. It's very common to see redundancy, 1 out of 2 and 2 out of 3, and then of course voting logic. Those devices being held accountable by the logic solver to see if they're telling us the right information. And then of course a subject that we could spend days on is proof testing intervals. And what is acceptable as a proof testing interval average and what is not is a whole nother discussion. We'll touch on it briefly here today. This is an example of an application with diversity. To the right-hand side, you'll notice that there are 2 transmitters, safety transmitter. Oh, these are 2 standard UE transmitters. And then off to the left-hand side, you'll see a mechanical switch. So it's a pretty clear example of what diversity is in our world. You've got 2 transmitters holding, each one held accountable, and then a mechanical device, which if it were going to fail would be quite a bit different than the other 2 devices. You know, it was commonly known that just a few years ago, maybe a decade, well, about 5 years ago, that there was an automobile manufacturer that had a problem with a gas pedal. And what is interesting about determining this problem was it was initially first thought it might have been a floor mat issue, which was not the issue. But once the manufacturer boiled it down and found where their problem was, it was a lack of diversity within their electronics. What they had done to save some money is they created 3 levels of electronics that were common mode. As opposed to prior to that, they had 2 levels with some diversity in their electronics. And so what happened was during manufacturing, if one mode of this gas pedal failed, they found that the other 2, which were put in there for redundancy, would also fail. It was called common mode failure in electronics. And so one of the things that we have to be aware of is this whole issue of common mode and common mode failure, and adding diversity to help minimize or mitigate that issue of common mode failure. Keep in mind too that human interface plays a major role in this common mode failure. So if I'm calibrating in, for instance, 3 of the same style transmitters, if I calibrate the first transmitter incorrectly, it's highly probable I might calibrate the other 2 incorrectly. So if I mix up and put some diversity and technology in there, I'm either going to catch it or at least one of these instruments are going to be correct. So the whole issue of diversity is extremely important. Redundancy is as important. We've all flown in airplanes, and you know, when you fly in an airplane, you may not realize, you probably do, that there are layers of redundancy within in the avionics of that airplane, from altitude to cabin pressure to hydraulics. There's a lot of redundancy within that airplane, and it's required because it's 30,000 feet in the air. So if one instrument goes bad, you need to have a backup instrument in there to keep this plane 30,000 feet in the air. So that's important. The example I give over here on the right shows some redundancy. I've got again I've got a safety, or I've got a transmitter, I've got a switch, both pressure and temperature. I've got backup redundancy here on this pump to make sure that what instrument A is telling me, instrument B is backing it up in case instrument A fails. So the redundancy is important, that I don't have a lapse in protection. Now, voting logic can also be important. You'll see the first schematic I've put up on the screen is 1 out of 1, or simplex system. The first channel, pressure transmitter, if it fails, leaves us vulnerable to our system being unprotected. So this could be, this is a system or a SIS that I see, but not so frequently, because it leaves the system unprotected should that transmitter or that final element have a failure mode to it. There's zero fault tolerance here. 1 out of 2, or dual channel, is probably the most popular. I've got 2 transmitters here, and these 2 transmitters are basically monitoring the process. I've got a safety PLC and a final element. So if one of these transmitters would happen to fail, I've got a backup, and if it's a good safety transmitter with a high safe failure fraction, it's going to tell that PLC it failed. At least I'm not running unprotected. I've got time to get out and repair the device. Now, there's a lot of discussion of, well, when we get into 1 out of 2 channels like this for an ESD, it increases the potential for nuisance or spurious trips, but it does also increase the integrity of the overall safety instrumented system. I'm not down without a potential protection to the safety instrumented system. Then, of course, we also know of the 2 out of 3, which is also extremely popular. I've got 3 transmitters, and these 3 transmitters are talking to the PLC. They're reporting their health condition. They're reporting their overall performance, and the PLC is checking the data that they're sending out against each other. So if one of these transmitters were to go off into Never Never Land via the namer output, then the PLC is going to recognize that and call it out, and then require some replacement, a replacement of that transmitter. So again, this is 2 out of 3. The drawback is cost. It's expensive. It's probably about the only drawback, very common in our industry. It does raise, of course, the one concern of spurious trips. However, again, the spurious trips come with protection. One of these transmitters happens to fail, we've got total protection within our safety instrumented system. This is really an interesting topic that probably will gloss over very quickly, because what happens oftentimes when I get into the discussion of proof testing and will your equipment work when needed, it generates a lot of discussion, because corporations have created their own proven in use standards as it relates to proof testing. However, for just the academic side of it, we'll address proof testing in this way, that an SIS system must be tested periodically to prove the essential components will work when needed. And then more frequent testing means, of course, greater assurance the components are in good working order, kind of, because it raises the cost. And I always still have this underlying question that keeps me awake at night, and that is that I just proof tested a device and put it back online, but did I really find it to have a problem? Because as soon as I could put it back online, it could fail. So what companies are doing, a lot of corporations are looking at this proof testing average, this interval, and trying to figure out for themselves what works best to lower the risk, and then how to do these proof tests. Keep in mind, when you proof test a device, you take it out of circuit. You take that safety instrumented system out of protection. So how long will that go? How long will it last? And then, of course, the major underlying question is really the higher the safe failure fraction, and the more levels of technology I can buy in a device to tell me it's working or not, could allow me to draw out or increase my time interval of proof testing. So the better the device, the longer that time could go. But again, that time and all that data has to come from that FMEDA. How well can I, or how can I rely on this device in order to stretch out the proof testing interval to it? So again, proof testing is a large discussion and requires issues such as the slide I brought up here, and that is, want to make it easier on yourself? Well, everybody does. You've got several options that you can consider. Design the SIS so that it doesn't need testing during long periods between plant shutdowns. You can save some dollars, and the only way you can do that, though, is to buy an instrument, purchase an instrument that has extremely high safe failure fractions. And what happens then is you do have a device that has a lot of accountability to it. So those are sometimes far and in between to find, but there's one option. Install bypass lines around each final control element to facilitate proof testing while the process remains in operation. You can do that. You have no protection during this test. Bypass lines may be inadvertently left open. So again, here goes our human factor. These are all very risky issues to consider. And then, of course, use manual or automated partial strokes for valves, which is not a subject we'll get into today. But again, these are all things that you have to consider when designing or servicing or looking at these safety instrumented systems. Now, there are some key drivers, key industry drivers, and these are the things, of course, that keep the owners of these and the CEOs of our companies up at night. The need for improved levels of safety. We are living in a day and an age today, folks, that I don't know about you, but I know my company it stays awake and thinks about it at night. If you've shopped at Target or Home Depot or used your credit card anywhere, the level of security is heightened as far as the susceptibility of our data and our websites and our intranets and so on and so forth exists. The lack of end user SIS and SIL understanding. This is still an industry that's evolving, and we're still learning more and more and more every day what works best in regards to the implementation of safety instrumented systems and SIL devices within there. Increasing the adoption of SIL certification instruments or instrumentation, and then the tens of billions of dollars of old legacy safety systems that are needing replaced today. Keep in mind that EXIDA and TUV and these governing bodies of 61511 keep evolving. The latest assessment to instrumentation today is EXIDA's or 61511 2010 assessment. And the 2010 assessment gets into some things that the old legacy devices never had to worry about. For instance, I'll use communicable devices as an example. Prior to 2010, it was very acceptable to use a communicable device, such as HART. But once the 2010 assessment was put into practice, it then called out that communicable devices are not assessed by, say, EXIDA or TUV. They're not assessed. It cannot be used as a means to detect or report a device's condition. And the reason for that is because the cybersecurity assessment of 2010 does not allow that. Anyone within a facility can walk up to a communicable device and make a change. Or anyone potentially can get through the firewall into the infrastructure of that organization and make a change to that safety instrumented function, and potentially increasing pressure, increasing BTUs, or whatever. We live in a world of cybersecurity concerns today, and it's playing out right now in 61511 and 61508. So we have a major concern about the design of these instruments. High cost and downtime has decreased safety by delaying system upgrades. Both switches and transmitters are currently used still. So retrofitting is more complicated in some cases. And then old systems are certainly prone to failure, depending on how you're running your proof testing intervals, and then in shutdown and turnarounds, replacing those old systems is costly. So these are some of the things that keeps my boss and your boss up at night, for sure. So the conclusion is this, that the process owners face an important question. How can I keep my process running as much as possible to maximize my profit, because I've got stockholders looking for their returns, but yet prevent any accident to minimize or to maximize my safety? And then, of course, a properly designed safety instrument system plays an important role in answering that question, providing the proper balance between uptime and safety. So design is extremely important when we get into safety instrumented systems. So I'm at a point that I want to pause for some questions if there's any, and then I'm going to move forward on the next piece of the puzzle here, and that is looking at some instrumentation and the different levels of SILs that are out there and so on and so forth. So, Michael, are there any questions?
We've got a couple questions. Yes, we've got some questions.
Great. And I hope I didn't say rated again.
You might have. I didn't catch it. One of the questions which I found kind of interesting here is, does time affect the SFF rating of a device, or the safety failure fraction?
Time does affect the safe failure fraction. And when you look at a typical FMEDA, and I'll use EXIDA for example because I'm most familiar with them. When you look at a EXIDA report, and I think, Mike, you said you had an example of that, we can we can open that up to tables 2 and 3 and on, and we have, I think there's 10 tables in there that represent this whole concept of failure rate or failure in time, FIT. So what happens is that when you get into the FMEDA reports, you'll see that these devices have a failure in time calculation applied to them. It's taking into consideration the layers of technology that Exida will allow for this device to report its health. I'll show you an example of that here in the next slide or two, but we can look at that, and the answer is it's time. And it does affect the safe failure fraction because, of course, the better calculation or the more checksums that you have in a device gives you a very good failure in time calculation, or strong failure in time calculation.
All right.
That is done that calculation, by the way, or those numbers are provided by the manufacturer, and well, they're provided by Exida, working in conjunction with the manufacturer of a device. Those can't be altered, they can't be tweaked. The number is the number. When you get this report, it has failure in time calculations in it. You got to use those.
Yep, I can show those when I pull up an Exida report here in a second.
Perfect. Yep.
Do you want to do your last slide, and then I can come back to this last question, because this last question is really where I went to pull the Exida report, and it's about combustion control systems.
Oh, that's a great one. I've done a lot of work in combustion control systems, and so why don't you
hit your last slide, and then we'll go ahead and get into that. For those that are pressed for time, and are not interested in combustion control systems,
sure.
And we may answer it. Bow out.
Yep, we may answer it also in the next couple slides too. So what I wanted to do is just also mention to you that if you're looking for some additional data and you're into studying on your own and digging out some of this stuff, my company, United Electric Controls, is a 61508 certified company, through IEC 61508 certified company through Exida. And so we have a great resource network, SIS resource network on our website, and our website is ueonline.com. And of course, you can certainly feel free to contact me at any time at spierce@ueonline.com. UE, if you're not familiar with us, we are about an 85-year-old company. We're headquartered in Boston, Massachusetts. We're the largest manufacturer in the world of industrial pressure temperature devices for alarm and shutdown applications. And so we started out in the industry manufacturing pressure switches, temperature switches, and we now manufacture transmitters also for the safety instrument and system world. We're privately owned still and located, as I said, in Boston. All of our manufacturing is located in Boston, Massachusetts. The products that we make specifically are these that you see in front of you. They are basically safety transmitters for pressure, temperature, and differential. They are all SIL-2 certified and SIL-3 capable by Exida, and they all carry a safe failure fraction of 98.5%. There is no other instrument on the market today for pressure or temperature or differential that carries that high of a safe failure fraction. The reason for it was this device did not start out to be a process variable device. It started out from its creation as a safety transmitter. So from the ground up, we created this thing to be a safety transmitter, and so by doing that, we were able to build in all of the checksums that we know the industry is looking for to create the highest safe failure fraction known in the industry of 98.5. And the way we do it is very unique. We have an analog output, which is a 4 to 20 namer output, and it saturates to low if there's any fault with the device. We also have a local indication for health and the process variable, but we added this I am working diagnostic digital output to the device, because what happens is in most devices, I'll use transmitters as an example, the 4 to 20 namer output does not have the ability to check itself for accuracy, but with the 1 series safety transmitter and the internal checksums that we have, we're able to watch that 4 to 20 and compare it to the published accuracy. If it were to drift off or change, the I am working digital output will indicate in a open state that there is a problem with either the device or that 4 to 20 milliamp output. And when that happens, you have that human interface, which is required in some industries. Outside of that namer output, you have that they have that digital output that indicates, hey, wait a minute, I know you're still getting information from that 4 to 20, but something's wrong. And it could be anywhere on this device that you get that. So we have those 2 outputs, but we added something unique to this thing. Because if time is critical in safety, then if I'm going to have to take a 4 to 20 milliamp signal to my PLC, from my PLC to a costly interposing relay in the MC center or to a solenoid valve, I've lost a lot of time in response. So what we did is we embedded a safety relay into this safety transmitter that's rated at 0 to 240 volt AC at 5 amps. So what you can do now is you could use this device to switch directly your final element and shave off time response. Or in some cases, this has such a high safe failure fraction, and if it's a standalone device, it can operate in lieu of using a PLC. So now you have basically a PLC with this human interface I am working output. The only thing you're going to use the namer output for is to get 24 volts to the device, and now you can switch your final element direct. And you don't need the PLC because you've got the I am working diagnostic output that you can run back to your basic process control and say, hey, I'm either healthy or I'm not. Now, how do I know if that solid state relay has switched? Well, we've also added a digital output to tell you the status of that solid state relay. So back at your basic process control human interface, you see the status of the device and you see the status of that safety relay output. The set point to that safety relay output is programmable in the front. Once the cover's off of here, it's password protected, and at that point you can program in your set point, your deadband, and then this unit is up and running, and you basically got a self-contained, out-of-the-box safety instrumented function that's kind of 2-in-1. It's the PLC and a transmitter going to the final element. So that gives you an idea of the device. This is where I was talking about, rather than taking the signal in most cases to the PLC and out to the final element, you can really just go right to the final element, and your response, speed of response is quite quick, quite fast. So that gives you really a nutshell into the basics of safety instrumented systems, a transmitter that has a very, very high pedigree for safety alarm and shutdown. So with that said, Mike, if you have any questions, we can certainly.
The last question we have is about the combustion control systems.
Sure.
And here's the question. The basic process control system would be considered a combustion control system. And
yes.
Okay, so we got that piece. And the SIS would be considered the burner management system.
Yes.
Okay. If you want to flip the screen back to me, I can pull up, and I just pulled up the Honeywell Flame Safety Relay to show people, you know, where you find the SIL information.
Super.
So if I can.
I'm going to change your presenter. You ready?
I think I can do it.
Oh, okay. Very good.
Yeah, I think I just did it. Okay, so let's see. If I take this, Is that shown on my screen now, the PDF? The RM7890 manual?
I don't see it.
Oop. How about if I click Show My Screen? Does that help?
There you go. All right.
Okay. So here's the manual to a typical flame safety relay product, and
Right.
I just happened to pick the Honeywell because
Sure.
the question was on flame safety.
Yep.
If you flip down to it, you'll see here that it says it's SIL-3 capable.
Correct.
But nothing in this manual does it say anything about SIL-3 capable except this little statement here. Okay.
Right.
If used in properly designed systems, see the form. Okay.
Right.
So now, if I can pull up this next document. Okay. Did my next document now appear?
Yes, it is. SIL-3
Okay.
capable
So,
rating.
So now you see the SIL-3 capable rating, and this is Honeywell's document on the SIL-3. Okay.
Mm-hmm.
Here is the Exodus certificate.
Correct.
Okay.
Mm-hmm.
And you'll see in the Exodus certificate it says, and I don't know all these acronyms. I'm not sure what HFT is.
Hardware fault tolerance of 0.
Okay, there you go.
Mm-hmm.
But if you go down further, somewhere in here it talks about
Safe failure.
there you go.
This has. If you look at the numbers that we're looking at right now, we have safe detect. These are failure in time calculations that have been provided by Exida. So what you're looking at is you got safe detected, safe undetected, and then you have detected, or you have dangerous undetected and dangerous detected. Okay. These numbers, and then if you look all the way to the right, you'll see safe failure fractions of 99.3, 99.3 for each. So it has a significantly strong safe failure fraction. It has very significant numbers as it relates to safe detected. So if you see that very first column says safe detected, right there, it has a very strong pedigree. And so what this thing is doing is electronically, internally, it's looking at itself, and it's going to give you a pretty good report back of anything that's, if you look at the dangerous undetected, the failure in time numbers, which are in billions of hours, is very low. So that would mean, you look at this device, it has a very strong pedigree, and
so any product, going back to somebody coming in and saying my product is SIL rated, you really got to come back to this.
You really do.
Absolutely. Which it's not really SIL rated. It's a certification presented by a third party that gives you the numbers that tells you how this thing's going to respond. And
really
that then gives you the SIL level that the product can operate at.
Exactly.
Right.
Exactly.
So it's never really a rating, which I think is one of the important things to take away from all of this.
It's a great takeaway, and of course, supporting documentation is the biggest question out there, and looking at that supporting documentation is critical.
Yeah.
And this is a perfect example of what that would look like. The UE numbers would look very similar to this. The charts tables would be very similar to how this folds out.
Yep. The last question I have.
Okay, go ahead.
The last question I have is there a DC rating for the device? And I think he's talking about the safety transmitter of the safety relay.
Right. There is not a DC rating, and for a very specific reason, that because of the size of the enclosure and the amount of what we wanted this device to drive, the I²T curve of that heat rise for a DC load would be too significant. So we could not rate it for a DC rating because of the inductive loads that it could potentially see. So it had to go the AC route, unfortunately, to give us that. And you know, the interesting scenario about the safety transmitter, I showed you the various layers of technology that it has. You could just use it as a simple analog output device in a SIL, SIL-2 certified or SIL-3 capable application. It can still be used, and you still have all of the, the accountability as far as failure of the device in a saturation. So the transmitter saturates to like 3.8 milliamps, and once it does, you know that that's a failure of the unit. You don't know what failed until you walk out and look at it, but you have indication it failed. But if you chose to use the additional layers, it's in there. And the thing to measure here is, we talked about cost being critical in safety, but all because you got a high price doesn't mean you have a highly reliable device. So this device that we manufacture sells for $800. So if you compare that against other transmitters in the market for safety instrumented systems, this really helps you build a system, say 2 out of 3, or voting logic that's reasonably acceptable or cost effective. But let's not forget diversity. And so common mode failure is a critical issue. So if you're using other manufacturers' transmitters and you're going 2 out of 3 or 1 out of 2, make sure that diversity is in there. So add a UE safety transmitter to your existing architecture. So you might have 2 of your current transmitters that you're now standardized on. Add this diversity, and diversity can give you quite a bit of good information all the way to that digital output, which can be used for human interface.
That's for sure.
So it's got some good options to it.
Yeah. Scott, thank you very much for your presentation. I think at this point we are out of questions. If anybody does have any specific application questions or would like to know more about the safety transmitter that Scott presented at the end, please feel free to give us a call at 800-9-LESMAN or 800-953-7626. If you don't know your account manager, feel free to ask for me, and I'll make sure that you get taken care of. Our next webinar is going to be in early December, and it's going to feature Lesman's own A.J. Pisker, and it's going to be on the theme of combustion systems. A.J. has over 10 years of experience with combustion applications, previously working for Honeywell and Maxon in their combustion businesses. He's going to go over Combustion 101. So if you have applications that use heat in your process, and you won't want to miss A.J.'s webinar. You can either sign up in the training center portion of our website or wait for the announcement to come out shortly. At this point, since I'm not seeing any other questions, I do appreciate everybody's time, and thank you very much for attending. We will be ending the webinar now. Thanks.